Thanks very much to the organizers for having me here. And everything I talk about is joint work with Ben Bakker and Jacob Tsimerman. Let Jacob X be Shimura data. And let S be dissociate Shimura variety. So throughout I'm going to suppress almost all notation. There won't be any G and X's, and my K will be implicit. I will assume that K is sufficiently small that primes away from the prime that we care about. For all of that, again, we expect all of that. As far as notation goes. Right, so at a first glance, this is a complex analytic space, and then Bailey and Borel proved that this is actually a complex algebraic variety. And Eileen, Min, and Borovoy show that this complex algebraic variety actually descends to a canonically defined number field. That number field is canonically associated to the Shimura data you start off with. This is a number of factors.
Sorry, I think you should really put Shimura's name on this.
All right. So let's give Shimura credit for all of this. The name also indicates that, you know, he's involved in. Sorry. Okay. So you start off with a complex analytic space. It ends up being a complex algebraic variety, which actually descends canonically to a number field. Now the next question is, can you have a nice theory of integral model? Right. In particular, let V be a place of E, and let's say it divides the rational prime P. And you want good models S over the ring of integers at the completion of E at your place V. Question is, can you construct good models? So, what is a good model? Let's call a model an integral canonical model. For short, an ICM. If it satisfies two conditions. First, we want it to be smooth. But this alone is not enough because you could just take your model over E, base change it to EV. That gives you a smooth model over OEV. So you want some extra, you want to satisfy an extra condition, and that condition is what I'm going to call an extension property. So there was the extension property as it's classically defined wasn't something obvious, but there was somewhat of a convergence to the definition of the extension property. So what I'm going to state is going to be slightly different, but it's morally broadly the same. I should say that the extension property was originally defined by Milne and refined by Moonen. Right, so the one I'm going to talk about is a bit different, but not, but only cosmetically so. So we say that S satisfies the extension property if for all, if you're given a map from the generic fiber of a smooth scheme over OEV to a Shimura variety. Such that the pullback of an appropriate local system extends to the integral model X then this map actually arises from a map of integral models. Now I haven't told you what this is. This is just an analytic local system on your integral model induced by an appropriate algebraic representation of the reductive group G that gives us to Shimura.
I'm sorry, what are the letters with the blackboard?
So this is
is it at?
yeah, this is H for et al. And this is L.
L, and then the middle, in the middle there is a letter. What is the name of the letter?
Over here? Or over
Is
here?
it V between N and L?
Oh, V. Oh, this is V. This is script V.
No.
Yes. It's a blackboard V. Can you make you happier? I can.
No. I once you told us.
Right? I should say that L over here is going to be different from P. So Milne and Moonan's definition is in terms of the tower. Yes.
Does this mean that the grid generic fiber of the p-adic completion of your S or script S must be the production locus or essentially crystalline locus?
Can you tell us again?
So in the previous talk, there was this notion of having an integral model whose like rigid fiber is some prescribed.
Yes. So you're saying will this mean that I see. So will this mean that the rigid general fiber of S, not capital S, but the rigid general fiber of S will be? Yeah, I think so.
So I guess the question is here also maybe does it depend which L you take, or is this independent of L?
This is independent of L. At least once your level is small enough at 1L, if you know this for 1L, you'll know this for every other L by companion. Alright. Okay. So let me perhaps talk about, okay. So before talking about an example, that's a conjecture of Rappaport. That if your level structure at P is hyperspecial, then there exists an integral canonical model.
Would it make Langlands here as well?
So I think Langlands also have a different conjecture. They have conjecture about the mod P point of Shimura variety. I thought this was due to just apropos, but I'm happy to add Langlands. In any case, if your level structure at P is hyperspecial, then you expect that there should be smooth models that satisfy this extension property. So before talking about general Shimura varieties or even Shimura varieties of Hodge type, let me talk about EG. So if your G is the group of symplectic similitudes, then your Shimura variety is going to be the moduli space of polarized abelian varieties. And if your level structure at P is hyperspecial, then the polarization is going to be prime to P. Okay. Then what happens? Then the modular problem allows you to define an integral model. And again, denote by AG or ZP. Grothendieck proves that the deformation of a prime to P polarized abelian variety is unobstructed. And this tells you that the model is going to be smooth. Now, what about the extension property? And let's start off with a smooth scheme X and a map from its generic fiber to AG. Now, under the condition that this, all right, so then in the case of AG, this local system is just going to be the relative Vital cohomology of the family of abelian schemes that AG carries. Saying that this local system extends tells you that your family of abelian schemes extends to codimension 1 points of X. This is the Ananth-Shankar criterion. Well, now you have an abelian scheme on X, but perhaps defined away from codimension 2 or higher points. A Chai and Falkings tell you that whenever you have the setup, your abelian scheme will extend to high codimension points as well. That gives you an extension of the map S to high codimension points. So you extended the map from the integral model to the integral model EG, and therefore this is an integral canonical model. Right now, let's say S is a Hodge type. What this means is that S embeds inside AG. Then Kisin defines integral models as follows. Right now, this is within the generic fiber. We've already seen that AG has an integral canonical model. Kisin defines the integral model associated to S to be the closure, to be the normalization of the closure of S inside the integral model of AG. Once you define it this way, the extension property follows formally from the extension property for AG. Because you have the extension property for AG, you have it for any closed subscheme of AG. But smoothness is extremely not found. And Kisin proves that this model is indeed smooth if given that Kp is hyperspecial. So Shimura varieties of Hodge type also have canonical models. Let me now make a couple of remarks. All these theorems go through even in the case of abelian type. Kisin also constructs integral canonical models for Shimura varieties which are of abelian type. So the Shimura variety is said to be of abelian type, that there's a finite cover of it which embeds inside AG, in other words, which is a Hodge type. And Yuriksu proves that the normalization step is not necessary. If you take the closure of S inside AG, that's already going to be smooth.
So what do you mean by pre-gradient type here?
So there's, well, for Shimura varieties of type D, which satisfy some conditions, the universal cover is the form of the group whose derived subgroup is strictly connected.
Yes.
That doesn't embed inside GSP.
Yes.
Like, that is a clear feeling that.
But you're saying that the Kissen constructs models for those things?
Yes, I think so. His methods don't work for that. So I think it's fairly formal that once you have, because you have return covers everywhere, once you have a smooth model for something, that's going to propagate up and down the tower. Perhaps I'm mistaken, but that was my understanding.
Yeah, sure.
All right. Yeah. Okay. All right. So these are most but not all Shimura varieties. Let me quickly talk about when these Shimura varieties are, when a Shimura variety is of abelian type and when it's not. So if you G, if the factors, simple factors of the group G that define the Shimura variety, if these are of type A, so if it's unitary, B, if it's odd orthogonal, C, if it's symplectic, and some even orthogonal groups, then your Shimura variety will always be abelian. But there are Shimura data associated to exceptional groups. And if it's of mixed type D, then it's not abelian. It's expected but not known that S still carries some geometric family, but that's not known, and even if S were to carry such a family, it would not arise from abelian varieties. So you can't really use EG to say anything about these non-abelian Shimura varieties. So S over E, remember E is a reflex field, is spread out any which way. Spread out to get an integral model, a global integral model. Then, first statement I want to mention, joined with Ben and Jacob, is that this spread out model is going to be canonical for all primes that don't divide a sufficiently large integer. So let me remark that the definition of an integral canonical model has two features. One has two properties. One is that it has to be smooth. The other one is that it satisfies the exception property. We can just formally obtain smoothness by picking it to be large enough. Because the Shimura variety is smooth in characteristic 0, any spread out model will be smooth for large enough times p. Unlike Mark's theorem, where he's able to pin down exactly what p your Shimura variety is going to be smooth at. But the extension property, which is formal for Shimura varieties of Hodge type, is not formal for these exceptional Shimura varieties. So the content of this theorem is that your global spread out model satisfies the extension property for large enough times. The smoothness is not the content of this theorem, the content is the extension property.
If you just knew, like, do you need the n greater than 1 except for smoothness, or like
No, we need it for
you
every.
need it for?
Yeah. But given what happens in the case of abelian varieties, given what happens in the case of AG and Shimura varieties of hot type, if I were to put money on it, I would guess that there should be some model satisfying an extension property regardless of how bad your reduction is. Because that happens for AG. You can use Adam's trick to see that. But of course, for smoothness, you do need, you do expect to not be smooth if your level is not high. All right. We're going to talk about a few applications. We show that these Shimura varieties satisfy an extension property. I'm going to talk about a different sort of extension. But first, for that, let me go to the complex numbers. So Borel proves that if you have, let D be the open unit disk. Borel proves that once your level structure is small enough, then any map from a product of punctured unit disks to your Shimura variety cannot have essential singularities. Then there's an extension with variable compactification of Shimura variety of G. And once you have this, you also get a very nice theorem that tells you that whenever you have a complex algebraic variety mapping to that gives you a holomorph that maps in a holomorphic way to your Shimura variety, then that holomorphic map actually has to be algebraic. You just take the appropriate compactification of the source and then use the fact that at the boundary this is what it looks like to extend the map to the compactification, and then you apply Gaga to reduce the algebraic speed theorem. So of course, we might ask a p-adic analog. Enjoyed work with Abhishek Oswal and Tsimerman along with the appendix by Ananth Patel. We prove a p-adic analog of Borel's theorem for Shimura varieties of abelian type. So if you let dp be the p-adic unit disk, and you take a rigid analytic map from a product of punctured p-adic unit disks and p-adic unit disks to the analytification of your Shimura variety, and if the map is defined over a discretely valued p-adic field. In fact, sorry, I need to assume that F is of abelian type. Again, pre-abelian is enough. Alright, so given such a map to a defined over a discretely valued p-adic field, then such a map has to extend to a map from dp to the a plus b to the analytification of the Bailey-Borel compactification of your Shimura variety. But our work very strongly uses abelian varieties in p-divisible groups and that of closing spaces, and so this theorem only works for the abelian case. But there is no restriction on what p is. P can be any time. Corollary of the proof of this theorem gives us a weakened version of the p-adic Borel extension also for exceptional Shimura varieties. So just for brevity, I'm going to state this theorem in the proper case, but we also have the result in the non-proper case. Take a proper Shimura variety, and of course, theorem is most interesting in the exceptional case. And let P be a big enough prime. Every map, not from a product, but just from P star to S, defined over an unramified direct field extends. Let me just say in words what our version is in the non-proper case. So if you add the extra condition that at least one point maps to the crystalline locus, then the map has to extend to D. So in the non-proper case, we need at least one point to map to the Goodruption locus.
Is the source of these restrictions?
Sorry?
What is the reason for these restrictions?
So we need that coming from here. So we use a version of the inverse Cartier transform, and for that you need to be defined over W mod P squared, and that's why we have this restriction. But hopefully we'll be able to remove this restriction eventually. I should also say that having one copy instead of multiple copies, that's not really a big deal. You could probably get rid of this, and we could also probably get rid of the proper / grid action assumption. Okay. All right. We also have applications to CN theory on your non-abelian Shimura varieties. So under these assumptions, in other words, your n is big enough. We show that for every take any point, take any FQ valued point of your integral model. I had way long ago, the beginning of my talk, mentioned an analytic local system, which we use to define our extension property. Well, that's going to give you an analytic local system on the mod P variety. And given that analytic local system, you can take the stock at your close point x, and you have a Frobenius action on it. And it's conjectured in full generality that whenever you have an irreducible arithmetic local system or a geometrically reducible local system on a variety defined over a finite field, then the Frobenius at every close point is Frobenius at every close point, that anamorphism is expected to be semi-simple, and we prove that's the case for exceptional Shimura varieties as well. So Tate proves this for abelian varieties, and therefore proves this for Shimura varieties of Hodge and abelian type. A consequence of this is that once you define the notion of special points correctly, every special point of a Shimura variety mod P, every point of a Shimura variety mod P is going to be special. We also show that the mu ordinary locus of the Shimura variety is non-empty. This was proved by Daniel Wortman in the Hodge and abelian type case.
How do you define the mu ordinary locus?
Sorry?
How do you define the mu ordinary locus?
We define it. We define a point to be mu ordinary if the Hodge co-character is the Galois average. No, Newton co-character is the Galois average of the Hodge co-character.
Are you getting some kind of p-adic local system?
We also have an S-crystal and everything given by Roshnik. I'm not doing that. But yes, that's exactly how we define the Newton co-character.
And what is the definition for special? Because you said if you define it correctly.
Right, so if you had abelian varieties, then you can just ask for abelian variety to have Cn. If you're in characteristic 0, you can ask for the Hodge structure to have commutative Mumford-Tate group. You don't have any of that in this setting. What is true is that if your point is a Cn point, your point is going to be a Cn point if and only if it's pre-periodic for enough Hecke operators. We use semisimplicity to show that every finite field valued point is pre-periodic for prime to p Hecke operators. Well, for enough prime to p Hecke operators.
And you use that as your definition for special.
Correct.
Thank you.
It's also tempting to define a point to be special if it admits a lift to characteristic 0 to a special point, but there are lots and lots of same abelian varieties that don't admit lifts to same abelian varieties in characteristic 0. So that's not the right definition, right?
This theorem doesn't require p to be large.
Oh, everything requires p to be large. Right. So setting as in that's good. And we also show that every mu ordinary point admits a canonical CM lift. This is analogous to the Tate canonical lift. We also show that if you've got two mod p points that are ordinary, not just mu ordinary, but that are ordinary with conjugate Frobenius, then they're isogynous in a suitable sense. And when I say suitable sense, here's what I mean. Take the canonical lifts, you get two CM points over a number field and therefore over the complex numbers. They both give rise to rational Hodge structures. Those rational Hodge structures will be isomorphic, assuming that your original ordinary points have conjugate Fabini. I'm not sure what to expect if your mu ordinary instead of ordinary because the CM type isn't necessarily defined by Frobenius. I wouldn't be surprised if this ends up being not quite true if you replace ordinary by mu ordinary. So what I'm going to do with the rest of my time is say a few words about this theorem and about this theorem. And I'm going to work in the case when your test scheme X is a curve. Now, if your Shimura variety mod P did not have any rational curves, then all of this would be fairly straightforward, as I'll make clear over the next few minutes. But let me first tell you. Okay, so first let me sort of tell you why your Shimura varieties don't have rational curves in characteristic 0. So take your Shimura variety in characteristic 0, and let's look at the complex points. Now, suppose you had a map from P1 to your Shimura variety. Well, your Shimura variety is uniformized by the connected components of Shimura variety are uniformized by Hermitian symmetric domains. In fact, the X that I talked about, and these are simply connected, and your P1 is simply connected, so you can always lift a map from your P1 to your Shimura variety to a map from P1 to the Hermitian symmetric domain. But these spaces are bounded. And there are no non-constant holomorphic maps from C to a bounded space, let alone from P1 to a bounded space. And so P1 to Hermitian symmetric domain has to be constant. So the map, any map from P1 to your Shimura variety in CAD 0 has to be constant. This is no longer true in characteristic P. This proof, of course, fails because you don't have uniformization in characteristic P. And it's not just a question of the proof failing. There are rational curves inside Shimura varieties mod P. And a quick way to see this is as follows. So let E be a supersingularity curve. It has a unique order P group scheme. The homomorphisms of this group scheme is GA. In other words, it's positive dimensional. And so the homomorphisms of alpha p cross alpha p is GA cross GA. So now if you want to look at maps from alpha p to alpha p cross alpha p, that's also going to be GA cross GA. Sorry. If you want maps from alpha p to alpha p cross alpha p, that's going to be GA cross GA. Now two maps will have the same quote-unquote image exactly when they differ by an element of GM. And so this gives a family of subgroups of alpha p plus alpha p parameterized by GA cross GA mod GM, and this is P1. So now you have a family of abelian surfaces over P1 by looking at E cross E and modding out by this subgroup. And you can do things with polarization so that this family will be principally polarized. So this gives you a map from P1 to A2. So your multi-Shimura varieties do have rational curves. So this makes matters a bit harder. I should say this is also the reason why not every, morally this is the reason why not every mod 3 point admits a CM lift. What you have is Shimura varieties have P1s mod P, but not in characteristic 0. In fact, Ogus and Vologodsky prove that if you take a P1 in a Shimura variety, you can't even lift it mod P squared. And they do this using semistability argument, and that in fact is a blueprint to prove a regression property as well as this Borel theorem. Using work of Groznik, and a nodal version of Langsheng Zhuo's explicit inverse Tate transform. We show the following. Show that you have C tilde a flat curve mapping to S not P squared. Such that if C is the mod P special fiber, and let's say that C admits a and a reducible component that's rational, proper reducible component that's rational. Let's take that component, take the normalization, that's going to map to C. Let's call that map to mu. Such that the number of nodes on C naught is small enough relative to the prime P. Then C naught to S is constant. In other words, whenever you have a setup where you have an OD curve and one of the reducible components is a P1 with not too many nodes, and if that lifts to a map or P squared, then that rational component has to contract to a point here. Right? So let me quickly say why this implies the extension property for curves. CRX, let's say the special fiber is some full curve. Now X might, we want to prove the X maps to Shimura varieties, might not. You might have to resolve the map from straight X to the generic fiber. So after blowing up a bunch of times, you will get a different model that does map Shimura variety, but after blowing up, you might have a bunch of new P1s. In fact, you will have a bunch of new P1s. Of course, they probably could have lots and lots of nodes. But there'll always be an extremal P1 that has exactly one node. And you can contract that using this theorem. This has to map in a constant way. And then this has to map in a constant way. Now this P1, which initially had 3 nodes, just has 1 node. So now this has to map in a constant way. So on and so forth. You just contract all your P1s one by one. And you show that this map actually factors to X in the first place. Now, how do we use this theorem to prove our Borel theorem? So let's take a D star and let's write it as an increasing union of annuli. Where an k has outer radius 1 and inner radius 1 over p to k. This maps to the Shimura variety. Okay. Now the special fiber. Okay, so now there's a canonical integral model. Well, there's a natural enough integral model for your annulus. It's going to be the rigid generic fiber of this form of scheme. Wxy mod xy minus k to k, take the p-adic completion, then take the rigid every fiber, that's going to give you this annulus. Now, if this integral model mapped to a Shimura variety, then I claim we win. And so it maps to S for every k. And here's why. If you were to look at this integral model, then the special fiber is going to be these two A1s. This outer circle will specialize to one of the A1s minus a node. The inner circle will specialize to the other A1 minus the node. And this interior part will specialize to the node. Now, if this integral model mapped to the Shimura variety, then that means that this entire open annulus is going to map to the residue disk over one point. And this is true for every k. So then that tells you that this entire open annulus, this entire open P star, has to map to the residue ball at one point. But then the Riemann extension theorem tells you that you can fill in this hole. Now, all we need to show is that this integral model and not some other worse one maps to your S. But that just follows from here because any other integral model will be got by taking this and blowing it up. You're going to get a bunch of P1s. Now, the extreme, they needn't be P1s with one node, but there'll always be a P1 with at most two nodes. And this works with a number of nodes small enough relative to P. So you can always contract P1s with two nodes, and you inductively proceed to contract all P1s, and you just left these two A1s, and then that tells you that this integral model maps to the integral model Shimura. All right. Let me stop now. Thanks for your attention.
Any questions for the speaker?
How is the theorem of analogues used in
A great question. So we need a 14-LFI module in order to run this theorem through. Ogus-Vologodsky also need a 14-LFI module to say that your P1 doesn't lift, and Grosche give us 14-LFI modules. They tell us that your flat bundle underlies a 14-LFI module.
But you said you need the more explicit version of the inverse calculation.
We need a more explicit version to deal with the nodal case. So Lam, Sheng, and Zhou explicitly write out what your inverse Cartesian transform associated to a vector with a flat bundle is. We follow that.
Other questions? So if we assume that you have a smooth model, where are the places that you still use sort of n very large in this argument?
Two places. One is we need a. Okay, so first of all, over here we need P to be large enough relative to the So we start out with the representation V of G. That's going to give us a flat bundle. A filtered flat bundle satisfy Griffith's sample totality. So filtration is going to live in some numbers. We first need P to be large enough relative to that. That's one spot. Another spot is we need A known Groznik's crystal unit so that nothing goes through. And their theorem is fairly inexplicit. It doesn't tell you how big P has to be. Though I think if you were very optimistic, you'd expect crystal unity as long as P is large enough relative to the weight and your level is hyper special. But yeah, so that's conjectural. And we also need the. Okay, so now we have a flat bundle that's going to spread out. Then look at the associate gradient. That's going to give you a Kodaira-Spencer map. That's going to be everywhere immersive in cat 0. So it's going to be everywhere immersive mod P for big enough times P. That's the third place where we need P to be big enough. So if we have crystal unity and smoothness and your Kodaira-Spencer map being everywhere versal, and of course this, then that's all we need. Yes.
In the ordinary case, do you have some version of like set date coordinates?
That's a great question. My grad student is going to be working on this, and we expect there to be some question.
There are no further questions. Let's thank the speaker again.